All right, back to covalent Lewis structures. I like to review covalent Lewis structures just by doing one. So let's do, I don't know, let's do NF3, folks. NF3. You got your periodic tables close by. Hopefully, first thing you want to do is add up all them valence electrons. So nitrogen, come to the party with 5. Remember the shortcut for getting the valence electrons. You number across the top 1 to 8. Skipping the transition metals. So 1, 2, 3, 4, 5, 6, 7, 8. Right? Nitrogen's family's got 5. Fluorine's family's got 7, but there's 3 of them, so that's 21. You got 26 electrons to work with. So that's step 1. Add up all of your electrons. What's step 2? Step 2 is the atom that comes first, unless it's hydrogen, is going to be your central atom. So we're going to put nitrogen in the middle. Boom. And then you need to connect everything to that central atom with a single bond. So we got 3 fluorines. 1, 2, and 3. Each bond is 6 electrons. You used up 6. You got 20 electrons left. Now what? Well, we got 20 electrons left. We're going to try and make everybody happy using lone pairs. If we run out, every 2 electrons are short, we're going to add a bond. But if we have enough, we're good to go. There are 2 types of people, thinkers and doers. A thinker looks at this and says, I need 6 here, 6 here, 6 here, and 2 here. That's 18 plus 2. That's 20. It's going to be good. A doer just starts spending. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. There is our Lewis structure for nitrogen trifluoride. Nitrogen trifluoride has 3 single bound fluorines to a central nitrogen atom. Each of those fluorines has 3 lone pairs, and the central nitrogen atom has a single lone pair. All right, I'm going to give you a couple to try, just some warm-ups here. It's a couple warm-ups, a couple warm-ups. Let's do, let's do SBR2. Let's do COH2. Carbon's the central atom. And oh man, let's do CF4. Give those a shot. We'll go over it in a couple minutes. Let's do it, folks. Here we go. So please, unmute, yell at me if you got any questions, okay, as I go through these, all right? So if we're going to do sulfur dibromide, that's 6 plus 14, that's 20 electrons. Sulfur in the middle, 2 bromines coming off of it, ka-chow, used up 4, got 16 left. Now there's 2 kinds of people, there's thinkers and doers. Thinker looks at this, says, I need 6 plus 4 plus 6, that's 16, life is good. Or a doer, 2, 4, 6, that guy's happy. 8, 10, that guy's happy. 12, 14, 16, that guy's happy. SBR2. Next up, COH2, we got 4 plus 6 plus 2, that's 12 electrons. Carbon in the middle. We got an oxygen coming off of it and 2 hydrogens. Okay, that uses up 6 electrons, leaves you with 6. And now you gotta look at it, you gotta be like, whoa, okay. We went over this at the very end of class last time. If we look at this, 2 kinds of people, thinkers and doers. A thinker looks at this, says that oxygen needs 6 more, that carbon needs 2 more. The hydrogens don't need any more. Remember, hydrogen is happy with only 2. As soon as hydrogen makes a bond, it is done. You will never put dots on a hydrogen. You will never double bond to hydrogen. You will never triple bond to hydrogen. Hydrogen makes a single bond and it is done. It cannot do anything else. So anyway, I need 8 electrons. I've only got 6. I'm short 2. Now, a doer gets there too. It just takes them a little longer, 2, 4, 6, and it's an uh-oh. Every 2 electrons you're short, you got to add a bond. Carbon in the middle, double bond that oxygen, folks. Hydrogen and hydrogen. This is formaldehyde. That's for my embalming fluid, right? That's formaldehyde. Okay, if you have the hydrogens at a 90-degree angle, that's fine for now. In fact, that top structure doesn't look anything like that either. It's bent. We're going to get into molecular geometries with that Vesper sheet that I gave you all on Thursday here in a moment. Any questions so far on SBR2 or COH2? How we doing? I'm wondering how that double bond went. We'll do some more with double bonds here in a minute. CF4, let's do that. So that's 4 plus 28 equals 32. We got 32 electrons. Carbon in the middle. Fluorine, 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 fluorine. Used up 8, leaves me with 24, right? 24 electrons. Carbon's happy. Carbon's got his 2, 4, 6, 8. Don't put any dots on carbon. Carbon's done. We got 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There it is. Carbon tetrafluoride, central carbon atom, bound to 4 fluorines. Each fluorine has 3 lone pairs. That's your carbon tetrafluoride. How we doing, folks? How we doing? All right. Let's give you one here. So in high school, if you took chemistry, your high school chemistry teacher probably had you doing dot diagrams, even for covalent structures. And that's okay, but the problem is that doesn't work for all covalent structures. But the method I'm teaching you works for everybody, okay? This structure here, that dot diagram nonsense would never work for. CO, carbon monoxide. I want you to try this guy. Hopefully you haven't been using dot diagrams to do this, like your high school chemistry teacher probably taught you, because you're going to be in trouble. But I want you to try CO. Give this one a shot. We'll go over in about a minute. Carbon monoxide. You got 4 for the carbon. You got 6 for the oxygen. That's 10 total. You're going to put a carbon and then an oxygen. You used up 2, got 8. 2 types of people. I need 6 here and 6 here. That's 12. 12 minus 8, you're short 4. Every 2 electrons you're short, you got to add a bond. You got to add 2 bonds. It's going to be a triple bond. If you are not a thinker, which is what I just went over there, then be a doer. There's nothing wrong with that. I was a doer. Now I'm a thinker. I see both ways. It's totally fine. We got 8 electrons. Start making people happy. 2, 4, 6. That guy's happy. 8. And it's a double. Uh-oh. Double. Uh-oh. Every 2 electrons sure you add a bond. Triple bond this bad boy. Dots, dots. So again, 10 minus 6 leaves you with 4. Lone pair, lone pair. That's a happy molecule. I don't care where you put the lone pairs. You can put them on the tops. You know, technically, if when we get into hybridization, the orbital that they're sitting in is coming out 180 degrees, so that you go there. But if you are doing dot diagrams, you will never get this Lewis structure. You don't stand a chance. Okay. Dot diagrams are not going to get you here. That's why we don't do covalent bonds with dot diagrams or covalent bonding with dot diagrams. Awesome, man. We're doing so good. All right. What else we got here? Oh, my goodness. What to do? Let's do some ions. Let's do some ions. Yeah. Yeah. Mm-hmm. Lewis structures for ions. A charge changes the number of valence electrons you have to work with. All right. So let's do a cation first. This, of course, is a polyatomic ion that you all memorize. That is ammonium. So here's how this is going to work. If it's a cation, I want you to think about what must have happened to this structure. Well, if it's a cation, it lost electrons. Cations, or, you know, to become positive, you must have given away an electron. So what we're going to do is we're going to do our electron count, 5 for the nitrogen, 1 for each hydrogen. But then we need to take one away because of the positive charge. Now, this gets wires crossed in some people's brains. Okay? You see a plus sign where you actually subtract from your electron count. I know, that's crazy. So 5 plus 4 minus 1, you got 8 electrons to work with. You got 8 electrons to work with here in ammonium. Here's another pro tip. If you ever add up, let's say you forgot about that plus charge. You add it up and you get 9. If you ever get an odd number of electrons, you should know something is wrong. Okay, is it possible to have an odd number of valence electrons in a structure? Yes. Those structures are called radicals, though. A radical is a compound that has an unpaired electron in it. They are really reactive. You don't talk about those until organic chemistry. So we are not dealing with radicals in this class. You should never have an odd number. If you end up with an odd number, it's probably an ion, and you got to, like, if it's a cation, subtract 1. If it's an anion, add 1 or 2 or 3 or whatever. Okay, so we got 8 electrons to work with. So we're going to do our nitrogen in the middle. We're going to have 4 hydrogens coming off of it. Uses up 8, 0 left. And we're going to put it in brackets. And we're going to put the charge on the outside. So that's how we do the Lewis structure for a cation. Okay, bracket the whole shebang, charge on the outside. Okay, when I was growing up, we used to be able to just do a quarter bracket with the charge. But now if you look in the textbooks, they encapsulate the whole thing in brackets. So ammonium. Okay, there we go. Let's do an anion. Let's do cyanide. Now, this is a negative ion, which means it has additional electrons. So when we add this up, again, we got 4 plus 5. That's looking like 9. But now I have an extra one. We have 10 electrons to work with. Why don't you try and build the structure for cyanide with 10 electrons? Give it a shot. What do we got here? Well, we're going to put the carbon and the nitrogen together. Use this up 2, got 8. If you're a thinker, you know we are in trouble. If you're a doer, here we go. 2, 4, 6, 8. I'm out. Once again, it's a double. Uh-oh. Every 2 electrons you're short, you add a bond. We're going to make that bad boy a triple bond with the lone pairs popping off of there. Very similar to the CO, which we just did, which is why I chose to do this again. It's an ion, so you got to encapsulate it in brackets and pop a negative charge on the outside. How are we doing? Did we get that one? Give me a thumbs up if you got that guy. A couple people. All right. Zach, Sophia, Kate, good. Brendan, Bree, awesome. I think it's time for resonance, man. Woo, my favorite thing. If we got that, I think it's time for resonance. People don't like resonance. They don't like it one bit. But I love resonance. And if you're going to take organic chemistry, you better fall in love with resonance too. Let's do nitrates. Don't work ahead here, folks. Need you to hang with me on this one. Nitrates. Let's get our electron count. So we got 5 for the nitrogen. Boop. We got 6 for each oxygen. That's 18. And we got 1 for that additional charge. That's 24 electrons to work with. We got 24 electrons to work with. All right, we're gonna put nitrogen in the middle, and we're gonna put 3 oxygens coming off of it. 1, 2, and 3. That uses up 6 electrons, leaves me with 18. I'm gonna give you a second to catch up. All right, and now we're in trouble. If you're a thinker, you see why. We need 6 and 6 and 6 and 2. That's 20. We only got 18. We need 20 electrons. We only got 18. We're short 2. If you're a doer, here we go. I got 18 to spend. 2, 4, 6, 8, 10, 12, 14, 16, 18. And it's an uh-oh. You are short 2 electrons, folks. What do you do when you short 2 electrons? You add a bond. Yeah, we got a big problem. Here's the issue, folks. Where do you put it? Where's the bond go? You see, here's the problem. Now, I believe on, Wednesday last week? Boy, that was a while ago. I believe on Wednesday last week, we did phosgene. Nasty little molecule. We ran into this same predicament, but there was a correct answer here. With phosgene, we needed to add a bond, and we said we added here, nature loves symmetry, internal mirror plane. Right? So hopefully you see how this structure is different. There is a correct place to put it. But if we look at nitrate, they're all the same. If I put the double bond here, internal mirror plane. If I put the double bond here, internal mirror plane. If I put the double bond here, internal mirror plane. What do? They are all equivalent. Well, that's resonance, folks. Resonance is when you have a structure where there are equivalent ways you could draw the molecule, okay? And you're not going to like this unless you like resonance, like myself. When this happens, you got to draw all the structures. And this is usually where people are like, oh, right? But it's all about mindset, right? Instead of being like, I have to draw this 3 times. You could be like, I get to draw this 3 times, right? And if you lie to yourself long enough, you start to believe the lie, right? I mean, this is fun, right? We're having fun, right? We're having fun here, folks. Okay, so you need to draw all 3 structures. Now, myself, personally, I like to start with the double bond at the top. That's just me. You do you, right? So 24, I've spent 8, leaves me with 16. So that's a 2, 4, nitrogen's happy, 6, 8, 10, 12, 14, and a 16, folks. Now, okay, what do you get out of this? Well, the nitrogen with the double bond, that oxygen here with its double bound to the nitrogen, that's got 2 lone pairs. The oxygen that is singly bound to the nitrogen, that's got 3 lone pairs. So what we gonna do? We gonna draw this sucker again. Here we go. But we need to put the double bond somewhere else. I like to move my double bond in a clockwise fashion. So I'm moving it down there. And now I'm going to rotate it over there. There's our 3 resonance structures for nitrate. Double bond at the top, double bond on the right, double bond on the left. What do we need to do? Well, now this is an ion and it's resonance. So you need to encapsulate the entire thing in brackets. And you need to pop a negative charge on the outside because it's a -1 anion. What else do we need to do? We need to do a resonance arrow in between the structures. What's a resonance arrow? A resonance arrow is a double-headed arrow. Looks like that. That's my resonance arrow. And this is the correct way to do nitrate. Okay, what happened here? We needed to add a bond, but there was no one correct place to put it. Okay, so what we had to do is draw all possible structures. Now, you're really not going to like this next thing that I mentioned. Here's the thing. Resonance is like a breakdown in Lewis theory. What does that mean? None of these are actually correct. The real answer is actually a hybrid of these 3. And we use resonance to try and show it. Here's what's actually going on. There's actually no double bond in this molecule, and there's no single bond in this molecule. That double bond spends a third of its time here. Well, that double bond, it looks like, would spend a third of its time here, a third of its time here, and a third of its time here. And when they first discovered resonance, scientists actually thought that that double bond spun around like a propeller. But that's not what we believe anymore. We actually believe that, that a third of a bond is everywhere all the time. So what you actually end up with is that double bond is shared by 3 molecules equally. So this is actually a 1 1/3 bond here, here, and here. It's 3 1 1/3 bonds. Okay, for the nitrate. Pretty crazy. I know. In high school, you learn that there are just single, double, and triple bonds, but there's 1 1/3 bonds, there's 1.5 bonds, there's 2 1/3 bonds, there's 2.5 bonds. Yeah, it's way more complicated than single, double, triple. Let's try another one. We just did nitrates. I'm gonna have you guys try nitrites, and I'll kind of try to help you along. I'll get you started. I love resonance. It's like literally my favorite thing. I love it so much. But I guess I could understand how people get hated. I don't know. It's not everything, to each their own. There's nitrites. Here's what I want. I want an electron count. And I want you to try to figure out if you have enough electrons. If not, how many bonds you're going to have to add. Then we're going to meet up and we're going to talk. So electron count, figure out if you got enough electrons to make everybody happy with lone pairs. Good luck. All right. We got 5 for the nitrogen, 6 for each oxygen, and an extra 1 for the negative charge. That's 18 electrons to work with. Okay, you're going to put nitrogen in the middle. You're going to have 2 oxygens coming off of it. Leaves you with 14. Here we go. 2, 4, 6, 8, 10, 12, 14. You are short 2 electrons, everybody. Every 2 electrons are short. You got to add a bond. We got to add a bond to this. Where do you put it? Well, here's the problem. If I put it on the left and I put it on the right, there's no difference. What do? Both. Okay, so we need to redraw this bad boy, and it is actually not linear, but we'll talk about that later on. It's actually bent. But you wouldn't know that till we get into Vesper theory, which is coming real soon. Anyway, we're going to add that double bond on the left. So we got 18 minus 6 now. You got 12 electrons left. This oxygen needs 4 more. Nitrogen needs 2 more. So I still have 6. There's my structure there. Why don't you go ahead and draw the other Lewis structure if you haven't done so? Go ahead. That is our Lewis structure for nitrite. Okay, boom, boom. Okay, what's actually going on here? Here's the crazy thing. There's not a single or double bond in this ion. What's actually going on here? It's actually a 1.5 bond on both sides, but there's no way to draw that. So what we do is draw the 2 Lewis structures and realize that it is a hybrid of those 2. Think about it. The double bond's here. It's a double bond half the time, single bond half the time. That averages out to 1.5. Single bond half the time, double bond half the time. That bond averages out to 1.5 bond. It's a 1.5 bond. Oh, and I didn't put the charge on the outside. I'd have lost a half a point. Right there. You forget that charge, will take off a half a point on the test. True story. All right. How we feeling? You want another one? Sure you do. Oh boy. Let's do carbonates. So that's
question. Does you're saying resonance only happens with polyatomic ions?
No, not saying that. Well, I'll tell you what. Let's switch it up. That's a wonderful question, Kristen. You know, the last 2 we did. A lot of polyatomic ions have resonance. Let me start with that. So there's a pretty good statement. A lot of polyatomic ions are resonance structures, but it doesn't have to be a polyatomic ion. Let's talk about this. This is an incredibly important little molecule right here. This is an elemental form of oxygen that exists in the upper levels of our atmosphere called ozone. So this is ozone. Boy, we were doing a number on this little bad boy here with our aerosols and our carbon tetrachlorides and our all that stuff, the CFCs. But this is like the one thing we can be proud of as a species. We were destroying that ozone layer, and ozone is important because it absorbs ultraviolet radiation, re-emits it, okay, and doesn't get all the way down to us. It kind of blocks that UV, and we were just chewing that ozone up. But we stopped putting that crap. Everybody stopped using those kinds of refrigerants. We stopped putting that crap in hairspray that would float up into the upper levels of the atmosphere and chew up the ozone, and it has almost completely rebuilt itself since the 90s. So we've done, it's like that one time we give ourselves a pat on the back. You know, there's a lot of things we can't do that for, but we did it, folks. Anyway, why don't you try ozone? Give this one a shot. I'm gonna, add up your electrons, and you'll see that resonance is not reserved only for polyatomic ions here, Kristen. All right, let's try this out. That's 6 times 3, that's 18. So we got 3 oxygens. So 1, 2, 3, used up 4, got 14 left. 2, 4, 6, 8, 10, 12, 14. Oh, you're short 2. What do? You can put it, you got to do resonance. Okay, because I could put it here, I could put it there. There's no difference. One is not better than the other. They are equivalent. So here we go. Now the true structure is actually bent. We'll get into why it's bent when we get to Vesper geometries. If you drew it in a straight line, it's totally cool. I just feel like drawing this beautiful molecule for real. So it's actually bent. These bond angles are actually less than 120. And then we're going to put the double bond on the other side. No charge here. It's neutral. It's not an ion. It's actually an elemental form of oxygen. Now, oxygen prefers to be O2, except for in the upper levels of the atmosphere, we got some strange chemistry going on. Okay, and there you go. The ultraviolet light catalyzes, makes this. There's so much energy up there in the upper levels of the atmosphere that oxygen can exist in the elemental state like this.